Quantum computing is often painted as mysterious and futuristic, but let me take you through it in plain language as if I were telling you a story. Imagine your regular computer as a diligent librarian, opening one book at a time, reading it, and closing it before moving to the next. That's how bits work. Each one is either a 0 or a 1. A quantum computer, however, is like a magical library where books can be open and closed at the same time until you look at them. This strange trick called superposition lets a quantum computer explore countless options in parallel. Think of it like guessing the combination of a 4-digit lock. A classical computer must try each of the 10,000 possibilities one by one, while a quantum computer can test them all at once and collapse directly to the right answer. Now, here's the challenge. Today's quantum computers only have a few hundred qubits, which are their version of bits. That's like a garage choir with 10 singers. Fine for a small tune, but nowhere near enough to perform a full-blown opera. To really solve hard problems like drug discovery, global logistics, or cracking encryption, we need millions of qubits singing perfectly in sync. But qubits are fragile. They're like spinning coins that topple over at the slightest breeze. And that breeze could be a vibration, a stray photon, or even a tiny bit of heat. This fragility is why error correction is so crucial. To keep one logical qubit stable, you might need 1,000 helper qubits watching it, so if one slips, the others pull it back. Scaling up becomes daunting. Millions of qubits might require billions of helpers, at least with today's designs. On top of that comes wiring. Each qubit demands its own microwaves, lasers, or magnetic nudges, and right now the wiring looks like a forest of pipes. 10 qubits, fine. 1,000,000 qubits, and suddenly you're trying to water 1,000,000 bonsai trees with 1,000,000 tiny hoses. That's why companies are thinking modular. Break the problem into Lego-like blocks of smaller quantum chips connected together. Cooling is another mountain. Qubits need to sit close to absolute zero, colder than outer space, or they lose their quantum magic. IBM and Google use dilution refrigerators, massive machines taller than a person, just to keep a few hundred qubits alive. Imagine trying to keep 1,000,000 scoops of ice cream frozen in the desert, and you'll see the scale of the problem. Yet the reason Google and IBM are so excited is because they believe they're within sight of making all this practical, building the first workable large-scale industrial quantum computers, and if they succeed, the payoff is enormous. Medicine could be revolutionized because simulating molecules at quantum levels could uncover new drugs. Finance could be transformed by optimizing portfolios with lightning speed. Artificial intelligence could leap forward with quantum-enhanced training. And yes, encryption, the codes protecting your bank, and national secrets could be cracked, forcing us into a new era of cybersecurity. So when these companies say they're nearing the milestone, what they really mean is that the finish line is visible, but the road is littered with hurdles. Scaling up the choir, correcting fragile voices, untangling the wiring jungle, and keeping the whole orchestra colder than space itself.